Hello everyone. Today we're going to be looking at factoring higher order power polynomials using long division. So what is a polynomial? I wanted to start there just as a quick little recap. You've already seen polynomials when it comes to quadratics. Expressions like 3x squared plus 5x plus 2 is a polynomial. Polynomials can also be binomials. Binomials such as 2x plus 4. These are all part of the same family of expressions in mathematics. And this is the definition that I kind of used off of Wikipedia. I modified it a little bit. A polynomial is an expression consisting of variables and coefficients. So like 3x squared is a coefficient 3 and a variable x squared, that involves only the operations of addition, subtraction, multiplication, and non-negative integer exponents on the variables. So what do they mean by non-negative integer exponents? Well, you can't have a power of -1 or a power of 1/2 if you're talking about a polynomial. So they have to be integers like 2, 3, 4, etc., etc. The general equation of a polynomial is usually written like this in math textbooks. I'll read it out to you here. It's a subscript n, x to the power of n, plus a n minus 1, x to the n minus 1, plus dot dot dot, plus a2 x2 plus a1 x plus a0. Now this looks probably a little bit confusing, but if you just look at the last three terms here, that would be a quadratic that you're used to seeing, like 3x squared plus 2x plus 1, for instance. So the a's just represent the coefficients that are numbers usually. These can be decimals. These can be all kinds of different values. They can be negative, positive. But if you look at the power here, it's an x to the power of 2, and then there's an x to the power of 1, which we don't normally write the 1. And then technically speaking, there would be an x to the power of 0 at the end here, but x to the power of 0 is just 1, so we don't normally write it. So why do we have all of these previous terms here, and why are the dot dot dots there? Well, that's because if you had let's say a polynomial that it had its highest power would be 7, and we usually call that a degree 7 polynomial. N would then be 7, but we usually have all of the descending powers all the way to a power of 0. So it would be x to the 7, and then x to the 7 minus 1, which would be x to the 6, and then the next one would be x to the 5, x to the 4, x to the 3, x to the 2, x to the 1, x to the 0. So it's just a way of listing all of the possibilities, and your a values would just be different coefficients. So I've listed that where a0 to an are just constants. Now another way of writing that equation, if we actually start from the right-hand side and work our way up to the left-hand side, this is a summation symbol here. It's the, I believe, capital letter epsilon in the Greek alphabet. And oftentimes in mathematics, if you have the sum of a bunch of things that are adding together that follow a pattern, you can simplify that by just listing what does each term look like in general. So a to the subscript k with an x to the power of k, that would be any one of these, okay? So for instance, this one here would be a2 x2, so when k equals 2, you would have that term. But the summation symbol says start at a k value of 0 and go all the way to a k value of n. So your first term would be a0 x to the 0, which is this term here. Your next term would be a1 x to the 1, which would be this term here, on and on and on, and you're adding them all up, which is what the summation symbol means. Okay, so I kind of simplified that over here. So you might see both of these expressions shown for what a general expression of a polynomial looks like. Now, we're going to be using long division in this lesson, and I wanted to start by recapping how does long division work. We haven't used long division in many years probably at this point in our lessons, so it's probably a good idea to just refresh our memory, and different teachers teach us different ways. This is the way that I was taught how to do long division. So let's say we want to divide 127 by 3. The long way of doing that is by setting up this little L-shaped line here, and basically what we're going to do is we're going to do operations below the line, and our answer is going to appear above the line. And the way it works is you ask yourself, digit by digit in 127, how many times does 3 go into the first digit here, which would be 1? Well, 3 doesn't go into 1 at all, so you would probably just write a 0 here, but we don't usually do that. We just leave it blank above. And you do keep things all lined up, so if we're working with the first digit, you're going to put the answer above here if there is one. And because there isn't a way that 3 can go into 1 without using fractions, we don't want to do that, you then go to the next 2 digits and combine them together. You go to the second digit and combine the first one with the second digit. And you say, how many times does 3 go into 12? Well, we know that 3 goes into 12 4 times. So we're going to put a 4 right above the 2 lined up to show that that's representing 12. And then what you do is you multiply the 4 times the 3, and you put the answer below the 12. What we're then going to do is we're going to subtract those two values. That's going to give us a 0. All right? So we figured out that 3 goes into the first 2 terms 4 times. Now we've got to take the next digit, which is the 7, and bring it down here and join it to whatever digit you had here. Now in this case we had a 0, so it's just going to be 07, but if this number had been a 1, you'd now have a 17 down here. So you're joining it together with these 2 digits. And then you ask yourself the question again, how many times does 3 go into 7? Well, 3 goes into 7 twice, so we're going to put a 2 here. We're going to multiply down. 2 times 3 is 6. And then we're going to subtract 7 minus 6, which is 1. Okay, now that 1, we could continue this process, and in elementary school when you learned about long division, you would have put a decimal here and you would have continued, but we're going to stop here because when we get into our polynomial long division, once we get to this number is usually when we stop, and this number is called the remainder. Probably should spell that right. Okay, so, and there are names for all of these values. You've got the divisor, you've got the dividend, and you've got the quotient. I'm not going to get into those things too much here, but what we've just shown is that we can divide 127 by 3, but we're going to end up with a remainder. So there's 2 different ways of writing the final answer here. We can either say that 127 divided by 3 is equal to 42, which is the numbers we got in our quotient up here, plus we've got to include what the remainder would be. Well, that remainder is a 1, but that 1 is actually divided by 3, which is the divisor. Okay, so you always have to include the divisor in the remainder. Now, another way of writing this is we could say that 127 is equal to 3 times 42 plus the remainder of 1. So both ways are acceptable. Usually the second way is a little bit more intuitive, but that is the way you would write the answer there. So we can do the exact same thing with a polynomial. So I want to divide x squared minus 4x minus 7 by x plus 5. And I've set up the long division below here. But I put a note here, and I want the note to be there so that when you reread your notes, it's one of the first things you see. We're going to see that sometimes when you're dividing polynomials by other things, that you might be missing terms. Like I could have written this as x squared minus 7 and, you know, said that the x term was like not there, right? But because you need to have all of your things lined up like we had in our previous slide here, you need to have a space for all of your possible powers in your long division. So if the minus 4x hadn't been there, we would actually have to write plus 0x as a placeholder for it. And I'll show an example of that a little bit later on. but for right now, we're going to just do this one as our starting one, and I'm starting with a quadratic just to make it a little bit easier to learn how all of this works. So I want to divide x squared minus 4x minus 7 by x plus 5. Well, let's use the same logic we were using above. What I'm trying to do is I'm trying to get a value here that when I subtract x squared by that value, my answer is going to be 0. I want my answer to be 0, okay? Well, that means I need an x squared in this position right here. So what do I have to multiply x plus 5 by to make sure that I get an x squared in this position? So I'm just going to erase this for now. And I'm hoping you can see that if I put an x here, when I multiply the x over here by x, I'm going to get an x squared in this position. And now when I subtract the two, that's going to give me a 0. But the problem is there's also a 5 here. And that x has to also multiply that 5, which is different from what we were doing with just numbers in long division. So x times plus 5 is going to be plus 5x. And now we're going to subtract down all of that stuff. Now I'm going to put a bracket here, and the bracket is there to remind me that I'm subtracting both the x squared and the 5x, and I'd strongly recommend you do the same thing. X squared minus x squared is 0. Minus 4x minus plus 5x would be negative 9x. And I've now successfully subtracted the two top terms in this section with the two terms that I just created by multiplying by x. And just like before, I'm now going to drop down this minus 7. Okay? So now I need a number here that when I subtract down, it's going to get rid of the negative 9x. Well, I need a negative 9x to appear there then. So we're going to go back up to the top here, and we're going to say, what would I multiply x plus 5 by to end up with a negative 9x in this position? Well, that would be a negative 9. So when I multiply by negative 9, and I'm going to start getting rid of these arrows here because it starts to get a little bit messy if I keep showing it, but the negative 9 is going to multiply both of those terms. So I'm going to end up with negative 9x, and then negative 9 times 5 is negative 45. So now I'm going to subtract down again, putting a bracket around all of this to show that the whole thing is subtracting. Negative 9x minus negative 9x is negative 9x plus 9x, which is 0, and I'm not going to write the 0. And then I've got negative 7 minus negative 45. Well, that becomes negative 7 plus 45, and that gives me 38. And once again, that is my remainder. Now, we're going to see later on that the remainder that we really want to have is 0. Okay, but for right now, you may not get remainders of 0. So what does this all mean now? Well, what was I doing? I was dividing x squared minus 4x minus 7 by x plus 5. And what did I just get as an answer? Well, I got excuse me, x minus 9 plus the 38 divided by the divisor, like we did before, of x plus 5. Or what we can do is write that x squared minus 4x minus 7 is equal to x plus 5 times x minus 9 plus 38. And this is actually the more powerful way of writing our answer. And that basically means that x plus 5 is not a factor of x squared minus 4x minus 7, because if it was a factor, my remainder would be 0. So let's look at one that I was mentioning before, what happens if you don't have all of your descending powers of x? Now this goes back to, and potentially links to another lesson on the sum and difference of cubes formula. It depends on how your teacher has taught your class, but this is called a difference of cubes here. So I want to use long division to show how I can divide a difference of cubes. So the problem is I've got some missing terms here. It's missing the x squared term and the x term. So I have to rewrite it as x cubed plus 0x squared plus 0x minus 27. And these are my placeholders. Okay, so I can't use my long division unless I have all of my placeholders for every possibility of the powers that would exist between x cubed and the negative 27 at the end here. So now if I set up my long division, I'm going to divide all of that by x minus 3. Okay, let's see what happens. So I need an x cubed here. So that means I'm going to have to multiply this by x squared. So I'm going to put an x squared here. I'm going to keep it lined up with the x squared, and now you can see the usefulness of my placeholder below. X squared times x is x cubed. X squared times negative 3 is negative 3x squared. And now see, you can see things are still lining up. All my cubes are together, all my squares are together. And I'm going to subtract downwards. That gives me 0. 0 minus negative 3 gives plus 3x squared. I'm going to drop my 0x, and then I'm going to start over again. So I'm trying to get rid of 3x squared. I need a 3x squared to appear here because I am going to be subtracting them. That means I'm going to multiply by 3x up here. 3x times x is 3x squared. 3x times negative 3 is negative 9x. I'm going to subtract down. 3x squared minus 3x squared is 0. 0 minus negative 9x is just 9x. Sorry, I used the wrong color there. Then I'm going to drop the minus 27 down. I'm just showing the arrows here to remind you that those are where those terms are coming from. And now I got to get rid of 9x. Well, to get rid of 9x, I need a plus 9 here. Plus 9 times x is 9x. Plus 9 times minus 3 is minus 27, and something very interesting happens here. When I subtract down, I end up with 0 as my remainder. So a couple of things. This is a really good example to show what happens when you don't have all of your terms with your descending powers of x listed. You just use placeholders with 0. But another thing happens here. Because our remainder is 0, that means that x minus 3 is actually a factor of the polynomial. And that means we can rewrite x cubed minus 27 is equal to our quotient times our divisor. So x minus 3 was our divisor times the quotient we got, which was x squared plus 3x plus 9. And if you've seen the difference formula for cubes, you will recognize that this follows that difference of squares formula. This is your AB This is your a squared, this is your b squared, and the signs follow the pattern for the signs of a difference of cubes. You'll notice that there's no remainder here. That's because our remainder was 0, and we have a perfect factor of our polynomial. Now, there's actually a faster way of doing long division, and it is called synthetic division. It is very similar to long division, but the main thing that we're going to do to save us time is because we know that we're supposed to have descending powers of x, x cubed, x squared, x to the 0, those letters are actually not necessary to write down. So a lot of synthetic division speed comes from just not having to write down every not digit, but every character in the expression. So we're only going to be working with the coefficients of the expression instead of the entire expression itself. So if we look at x squared minus 8x plus 7 divided by x minus 1 as our example, what are the coefficients to x squared minus 8x plus 7? Well, it is just 1, negative 8, and 7. In order for this to work, what we need to do is we need to find the root or the 0 of the divisor itself. So x minus 1 is what we're dividing by. If I make that equal to 0, we're going to get x equals 1 as our answer. You'll see where that x equals 1 comes into play in a second. So in order to set this up properly on a page, what you want to do is once you've listed your three coefficients of your dividend, you're going to skip a line on the line page, okay? Because you're going to be writing stuff in there. And here's your first introduction to how synthetic division works. Now, a lot of this is just learning the process. It is going to be the same as long division in the end, but this is the process. So you take the first number, you drop it down past that line that I said was going to be there, and you write it below here, okay? Then, and actually I'm going to do that in a different color. So let's use purple for that. Then what you're going to do is you're going to multiply that value times the root that we had over here. So we're going to multiply that times 1. And you write the answer below the negative 8. So 1 times 1 is 1. Then you subtract down. So this is where it starts to look similar. Sorry, I made a mistake. Normally, in long division, you would subtract down. In synthetic division, we're going to add down at this point, okay? So that is a little bit of a change, but it's kind of a similar setup, right? Where we are working downwards here, but we're going to add down. So negative 8 plus 1 is negative 7. Then we're going to multiply upwards again. And we're multiplying by the root that we got earlier, which is 1 here. So negative 7 times 1 is 7. Sorry, negative 7. And then we're going to add down again. And that gives us 0. So what does that all give us? Well, what it gives us is these two numbers, the 1 and the negative 7, are the coefficients of the letters that we would get, or the variables that we would get, if we divided x squared by x and x by itself, basically. Okay, x by x as well. Because you're dividing a quadratic by a term that has an x minus 1, overall, you're dividing all of the variables by x. So x squared divided by x is x. X divided by x is 1, so that doesn't appear here at all. And your coefficients are 1 minus 7. This number here is your remainder. So I now know that if I divide x squared minus 8x plus 7 by x minus 1, that gives me x minus 7 with no remainder. In other words, x squared minus 8x plus 7 can be written as x minus 1 times x minus 7, which we could have done by just factoring. Factoring this quadratic, two numbers that multiply to 7 and add to negative 8 would be negative 7 and negative 1, and that gives me those two roots as well. But I wanted to show you with something that you're familiar with first before we start getting into higher order polynomials. And that's how synthetic division works, okay? So synthetic division, again, you take the coefficients of your dividend, you write them down, you find the zero of your divisor, or the root of your divisor, you write that down, you slide the first coefficient down past a line on a line page, write it down again, and then multiply diagonally up by your zero or root. And then in one of the biggest differences between long division and synthetic division, you add those two numbers down to get your next number, multiply up by your root, add down to get your remainder in this case, and then whatever your answer is here, separated from your remainder, are the coefficients of your quotient. So let's try one that's a little bit different here. Now for this one, I'm actually going to do it both ways. I'm going to do it with long division, and I'm going to show you with synthetic division what it looks like as well. So let's start with long division. Maybe I should mention what is different with this case. The thing that's different with this case is we have a coefficient in front of x here in our divisor. So going to the long division here, the first term I need down below here is going to be a 3x squared to get rid of the 3x squared above. I already have a 3x over here, so if I multiply it by x, x times 3x squared gives me 3x squared. X times 4 gives me 4x. I'm going to stop using color at this point. We're subtracting down. 3x squared minus 3x squared is 0. 25x minus 4x is 21x. I'm going to drop the plus 28. I got to get rid of a 21x. I've got a 3x over here. I need a 21x to show up. I'm going to put a plus 7 here to do that. Plus 7 times 3x is 21x. Plus 7 times 4 is plus 28. Subtracting down gives me 0, which is beautiful, because that means that x plus 7 is a perfect factor of 3x squared plus 25x plus 28, and so is 3x plus 4, which was the divisor in the first place. So again, that means that I can write my answer 3x squared plus 25x plus 28 is equal to 3x plus 4 times x plus 7. Okay? Now let's see how synthetic division works. Now the first thing I'm going to need is I'm going to need my 0. Okay? Now my 0 comes from 3x plus 4 equals 0. So now I'm hoping at this point that some of you are getting to the point where you don't need to do all of the algebra. You can clearly see that the plus 4 is going to go over to the other side and become a minus 4, and then we're going to have to divide by 3. So minus 4 over 3 is my 0. And it is a fraction here, so I am going to have to carry this fraction around in the synthetic division. So I'm going to bring the 3 down. Again, I'm not going to use as much color as I did before. I'm going to multiply 3 times negative 4 over 3. Let me rewrite that a little bit better. Now negative 4 over 3 times 3 is just negative 4. I'm going to add down. So that gives me 21. And notice I'm adding down instead of subtracting down. But notice how I got the same 21 as I did over here. Okay. And then I'm going to multiply again by negative 4 over 3. Now 21 times negative 4 over 3, well 21 divided by 3 is 7. 7 times negative 4 is negative 28. And lo and behold, once again, adding down, I almost made the mistake, I'm going to get a 0. And there's my same remainder as I got over here. The problem is, if I look at these two coefficients, this is giving me 3x plus 21, which is not the same as the x plus 7 that I got as my answer. And when you have a 0 that has a fraction, at the very end, you must divide these factors, or these coefficients, by the 3, which is the denominator of the 0, to get your final answer. So if we divide by 3 here, divide by 3 here, then we're going to get the x plus 7 that we got up here as well. So that's a little bit of a tricky thing that you have to do if you have a divisor that has a number in front of the x. You're going to end up with a fractional 0, and at the very end of your synthetic division, you also have to divide by that denominator in order to get the correct answer for your quotient. And because of this reason, some students prefer to use long division. I mean, I do feel that synthetic division is faster, but you do have to remember that it's an adding down and this new thing about dividing by your divisor here, or your denominator here. So some students will always want to use long division because of that. And long division can be used in places where synthetic division can't. If you ever have like a cubic divided by a quadratic, for instance, you have to use long division, because you can't do a quadratic with synthetic division, okay, as your divisor. So there are benefits to both. I use synthetic division when I'm using anything that has to do with quadratics or cubics divided by terms that have x in them, like binomials with x in them, that don't, even if they do have a number in front, I will try to remember, but I have myself forgotten to divide by this 3 in the past. So usually I only use synthetic division if I'm dividing by something like x plus 5. Okay, I won't use it if I'm dividing by 3x minus 4. So it's really up to you at this point to decide which one is better for you. And that's going to be it for today's lesson. So I've now introduced long division to factor, and just to maybe give you a little bit of understanding of where we're going with this, I kind of mentioned it at the beginning of the lesson. Factoring leads to finding zeros. So if we know our zeros for our polynomial, if we have to graph our polynomial, we now know where the graph crosses the x-axis. And that's where we're heading with this. If you have higher level polynomials, factoring them will give you those zeros. So we'll see that in a future lesson. That is all for right now. Have yourselves a great day.